Pieter Claeys from the University of Cambridge as our next speaker. Peter is currently a research associate at the University of Cambridge. He completed his PhD from the University of Ghent and subsequently was also a postdoctoral researcher at Boston University with Professor Anatoly Polkovnikov. It's a pleasure to have Peter speak to us on thermalization and scrambling in dual unitary circuit models as part of our workshop. So let me hand over the floor to Peter with that.
Okay, thanks a lot for the introduction. And I would also like to again thank the organizer for putting together this excellent program and also for putting my talk so early so I can focus on all the other speakers without having to worry about my own talk. So I'm going to be highlighting some of the research from these two papers, which I wrote in collaboration with Austin at the University of Cambridge. And I was going to be presenting some preliminary calculations, some exploratory results, which were done in collaboration with Jonah Herzog-Arbeitman, who is an MPhil student at the University of Cambridge and has now moved on to Princeton. So a brief overview of what I'm going to be talking about. First, I'm going to give a short introduction to correlations in unitary circuits, and more specifically dual unitary circuits, which is what initially attracted me to this problem. After that, I'm going to be talking about our recent parameterization of some special class of dual unitary gates, which is also going to be related to the previous talk, before moving on to out-of-time ordered correlators and then presenting some preliminary results, also leading into the next talk on perturbed dual unitary gates. So before I kick off, some short introduction to why I'm actually interested in these unitary gates and what my approach is. So I started out being interested in general quantum many-body dynamics, where we typically characterize dynamics by looking, for example, correlation functions. So here I consider some correlation functions between two operators rho and sigma, which you can think of as, for example, Pauli matrices, one on side 0, one on side t, side x, and I let one evolve in time. And then if I look into how these are correlated at short times, if I let them evolve using, for example, some local Hamiltonian or some unitary circuit, they're going to be uncorrelated, zero correlator. Then after some finite time, they're going to become correlated. And at long times, the correlation is going to reach some steady state value, which is known as thermalization. We just have three regimes. First, have this causal light cone, where it takes a finite time for the correlations to become non-zero. So we can define some kind of causal light cone velocity. Then we reach the steady state value, which is typically only set by the conservation laws present in the system. And this is typically extremely hard to calculate in general many-body systems because of the exponential size of the Hilbert space. But within these unitary circuits, we can actually make a lot of exact statements, which I wasn't expecting to be that we were going to be able to do. So we want to use unitary circuits as a proxy for many-body dynamics. So I'm going to be considering time evolution generated by unitary operators acting on two sides. And graphically, these are represented in this way. So I have a unitary gate, which is just this blue square with two legs coming in, two legs coming out, and this Hermitian conjugate, which is the red square. And I'm going to consider a so-called brick wall circuit. So we can construct a general unitary evolution operator in various ways from such elementary building blocks. But we can construct the circuit in this way. And basically the number of layers here acts as some kind of discrete time step. And they act on some one-dimensional lattice. So here we have sides 1, side 2, side 3, side 4. So we essentially generate a discrete evolution in some discrete lattice. Now, I saw that there were quite a lot of students also present in the audience. So I want to make a brief detour and use this graphical notation. Also because this is one of the first talks of the workshop, and I imagine this is going to show up in multiple talks. So what we're doing is we're representing vectors and matrices and tensors as diagrams, where the number of indices necessary to specify the elements equals the number of legs of this diagram. So if I have a single vector, I can characterize the vector elements by a single index. So I can just represent this as a circle with a single leg sticking out. I have a matrix. I have two indices that are used to determine the elements. So I have one leg coming in, one leg coming out, so two legs. So in general tensor, I can have an arbitrary number of indices, so I can have an arbitrary number of legs sticking in and sticking out. And this is very useful for bookkeeping if you multiply something, which if I multiply a matrix with a vector, basically I'm taking two indices to be the same and summing over this, which in this graphical notation simply boils down to connecting legs. So multiplying this matrix with a vector gives me another vector. I can represent it graphically in this way, simply introducing this notation for matrix element MAB, vector element VB, and just take the summation. And for convenience, I'm going to drop all the indices of the outer legs And there's an implicit Einstein summation over the connecting legs. So multiplying a matrix with a vector simply can be represented in this way, which is very useful if you're considering diagrams looking something like what I've shown here, because we're essentially just multiplying a lot of vectors, a lot of tensors acting on two sides. So we're considering dynamics generated by such unitary brick wall circuits, and I'm going to be interested in calculating correlations for such problems. And so what I'm going to be doing, I have U dagger rho U. So U here is this full brick wall circuit. I have some operator rho, which you can again think of as a Pauli matrix, which acts on a single side, and then it just acts as identity everywhere else. So graphically, I can represent this in this way. So I have U dagger, this circuit constructed out of red gates, then my single operator rho of 0 acting on a single side, and then I have my unitary circuit here. And this can be thought of as some approximation of this local operator evolved with some local Hamiltonian, or just circuit representation. But the nice thing is that this has an effective light cone baked in, so it takes a finite time for correlations to propagate in these unitary circuits. Because you can see that here, we're essentially multiplying unitary circuits with their Hermitian conjugate. And because these are unitary, this is going to give me the identity. So I can just get rid of these circuits and just replace them by two lines. I can do this everywhere in the first layer. And then I see that by simplifying the diagram, I've again introduced multiplications of unitary gates with their Hermitian conjugate, which I can again remove, and so on and so on. And I can show that if I evolve a single local operator using such a unitary brick wall circuit, I get this kind of hourglass shape where the full support of this operator is determined by the number of discrete time steps. And so everywhere outside of this hourglass shape, this just acts as identity, so it acts completely trivially. So there's going to be zero correlations outside of this causal light cone, which is neat. So we reproduce this one feature of just correlation in generic many-body systems. And we're interested in calculating now correlations exactly on the light cone. So I'm still considering general unitary circuits, not specific unitary circuits. And I consider correlations that are essentially taking the trace of my time-evolved operator with some other local operator called sigma on some position x. And here I'm going to take this operator to be located on the outer edge of the light cone, so a distance t away from my initial operator. And this is just one kind of correlation I can calculate. And so I have this simplified diagram, this hourglass shape. Then here at the bottom, I multiply with my single operator on side x. And I'm taking the correlation at infinite temperature, essentially, which is taking the trace, which is simply connecting all these upper legs to these lower legs. And if I do that, I see that I've again introduced multiplications of unitary gates with their Hermitian conjugate. Now by connecting them this other way around, I can again simplify this. And again, I can do this trick where I just keep removing unitary gates, only using unitarity, till I end up with a diagram that looks something like this, which we started from unitary circuits, which had an infinite number of gates, because we could in principle work with an infinite lattice. And now with the number of gates we end up with is simply twice the number of time steps. So we have these correlations, and I can just write them in a slightly simpler form, just by taking this expression and moving the diagrams around, which doesn't really change the graphical notation. So if I want to calculate the correlations on the slide cone within this unitary circuits, which is going to be the main object of interest in the first part of my talk, I can simply do it in this way. So I start with my initial operator rho, then I act on it with this combination of my unitary circuit and its Hermitian conjugate, which are multiplied in some very specific way. And I do this t times, where t is the number of time steps. This is extremely convenient because we can simply identify this one building block here, which is this combination of the unitary gate and its Hermitian conjugate. This is so-called quantum channel M, and it just satisfies all the properties you need. If I want to calculate the correlations on the light cone at some finite time, I simply need to act on my operator rho with mt times. And I can do this for arbitrary times if I can diagonalize M, if I know its eigenstates and eigenvalues, which is the same way we typically approach dynamics within quantum mechanics. But the interesting thing is that while we started from an infinite Hilbert space with an infinite number of lattice sides, here, if I have a local q-dimensional Hilbert space, so if I were working on qubits, I would have a local two-dimensional Hilbert space. This quantum channel M acts on two copies of the local Hilbert space. So this is a q squared by q squared matrix. So for qubits, this is a 4x4 matrix. And you can just diagonalize that even by hand if you want to. So we can calculate correlations to arbitrary times within unitary circuits exactly on the light cone, where we only need to diagonalize this quantum channel. I can also have some notion of a steady state, because if this quantum channel has eigenvalues with modulus 1. If I apply this an infinite number of times, we're essentially just going to end up with a projector on the corresponding eigenstates. So by analyzing the eigenvalues of this quantum channel, we can really fully characterize the steady state, which is something that was pointed out by Bruno Bertini in a paper. But that brings me to dual unitary gates. So everything I've shown you in this derivation so far was completely general, so only really needs unitarity. But dual unitarity is much stronger, as was also pointed out in the first talk. And this is important because typically, if we want to calculate correlations inside of this causal light cone, they become intractable. We can still construct some kind of quantum channel formalism, but now instead of having a 4x4 matrix, it's going to grow exponentially. But if you have dual unitary circuits, then we can interpret these as being unitary in time. So I've shown you this hourglass shape arising simply from this unitarity identity. But we can also interpret them as being unitary in space, which is where the dual part comes in. So instead of interpreting this as generating evolution in time, I interpret this as generating evolution in space. I still end up with a unitary circuit. So I'm also going to have a causal light cone in space. And so it's a very simple derivation, which was initially highlighted in this paper here, to show that the only non-vanishing correlations within dual unitary circuits are exactly the ones on the light cone, which are the ones we can easily calculate using this quantum channel formalism. So that now brings me to some of our work. We basically showed in this paper here that there's a very specific class of dual unitary gates that we can parameterize for any dimension of the local Hilbert space. So we have quite a large playground of dual unitary gates, and we can all write them in this way. I mean, again, within this class, the organizers of this conference have found some additional classes which are really interesting. So just to take you through what's happening here. So this is very similar to this canonical form that we saw in the previous talk, but now just for arbitrary local Hilbert spaces. So you can just have a generic unitary gauge just acting on a single side or a single copy of the local Hilbert space. So U plus, U minus, V minus, V plus. And these can just be any local unitary as long as it acts on a single copy of the Hilbert space. And then the interesting part is this entangling gate, V of J, where J is some matrix which has the dimension of your local Hilbert space. Essentially, if we define this in terms of its matrix elements, we have some delta functions and some phase, which is completely general. And what this does, it acts as a swap gate or a permutation operator with an added phase depending on the input. So clearly, a swap gate is unitary and dual unitary. But here, by introducing these added phases and these one-side unitaries, we kind of move on from the simple example and get some interesting dynamics. And so to show that this is dual unitary, it's relatively easy. It's exactly the same as showing this is unitary. And we can think of this as a gate, but we can also think of this as some Floquet model where we evolve the system in time using some local Hamiltonian, then simply switch between evolution on the even sides and the odd sides after staggered times. So if I simply have the permutation operators on the entangling gate without phases for a local two-dimensional Hilbert space, so for qubits, I can write the swap gate in this way, which is just some Heisenberg interaction between neighboring qubits. If I do this for qubits, so a local three-dimensional Hilbert space, I can again write this as in terms of some Heisenberg interaction and some Heisenberg interaction squared. So this is just to point out that the swap gate can always be realized as some local Hamiltonian with nearest neighbor Heisenberg interactions. Then if we want to add the additional phases, these simply boil down to some Ising interactions. And if we want to introduce the additional one-side unitaries, U plus minus, V plus minus, we can simply do this by applying some local magnetic field in any arbitrary direction. So this gives us a class of unitary circuits satisfying these nice properties, where we have a lot of free parameters to play around with. And the rest of my talk is essentially going to be seeing what we can do with these parameters, both for correlations over these quantum channels, which should tell us something about thermalization, and for these out-of-time order correlators, which should tell us something about scrambling. So I can just plug in this parameterization in the quantum channel, and I have something very simple. So I have this
Peter?
quantum channel. Yes.
Peter?
Yeah.
The previous one, the characterization of Q, this one,
Yeah.
uh,
Yes.
how is it related to what Carol showed uh, one set of unitary operators? So is it immediately seeable, these two relation, or is it equivalent?
No. So I don't think there's an easy correspondence. The only
Okay.
correspondence is for qubits, where this parameterization is exactly the same as this canonical Cartan form that was
Yes.
presented there. But I don't know how this extends to
Okay.
how this relates in more general dual-unitary gates, which is
Okay.
a question I was fully expecting, but also know I was going to be able to answer.
Okay. Okay. Thanks.
Yeah. So we can plug this dual-unitary parameterization in this quantum channel, and basically half of the unitaries, so U minus and V minus drop out because we're considering correlations along positive light cone. So we only have a single U and a single V. So this is U plus and V plus, but I've simply renamed them U and V for convenience. So here I have U dagger U, here I have V dagger V. And this middle part is simply the quantum channel I would get if I only generated quantum channel from this entangling part. So you can really neatly separate the effect of the one-side unitaries and the entangling part. And the thing that really surprised us when we started looking into this parameterization, if you look into the quantum channel, only for this entangling gate, so only for this glorified swap gate, then this is diagonal, which means that here we have something which corresponds with some unitarities multiplied with something diagonal, multiplied with some other unitary operator, which is exactly the Schmidt decomposition or the singular value decomposition of our quantum channel. So by knowing this parameterization, we know the singular value decomposition of our quantum channel. And it's diagonal. I can just write down the eigenvalues sigma of this entangling gate, which are going to be the singular values of the full gate. And they only depend on the phases. And the eigenstates of this diagonal channel are simply the basis matrices, so simply operate with a single non-zero matrix element. So for example, matrix element A, B is non-zero. Then the corresponding singular value or eigenvalue, simply this sum over phases with factor 1 over q. And the only thing that's really interesting here, or not interesting, that I kind of want you to take away, that these are phases. And so if these phases, if A is different from B, this is going to give you something that's smaller than 0. So an eigenvalue or a singular value that's smaller than 0, so decaying. But if A equals B, so here, if this eigenoperator just has a single diagonal element, then the corresponding eigenvalue or singular value is going to be 1. Now, these are not going to decay, so we can have some notion of conservation loss here, which is going to be interesting if we want to make the connection with ergodicity and non-ergodicity. But so we have singular value composition, and now we want to see what kind of dynamics we can get by simply tuning these parameters. And if I take everything to be very simple, if I choose my singular value decomposition to be actually the eigenvalue decomposition, so I choose the left and right unitaries to be identical, I can even choose them to be the identity for simplicity, then all diagonal matrices are conserved because these are exactly the eigenvalues of the quantum channel of this entangling gate with eigenvalue 1. So you can simply write the gate as this sum over diagonal matrices, so projectors on diagonal matrices, plus some decaying corrections. These non-decaying eigenstates fix the long-time correlation. So if I want to know the long-time value of any correlations, I simply need to project on these non-decaying eigenoperators. And because I have multiples, I simply need to take a sum over these, which are fortunately already orthonormal. I end up with just a steady-state value of the long-time correlation, which looks something like this. And now, the precise form doesn't really matter, but just to show that something that really depends on all of the diagonal elements of both your initial operator and your final operator. So this is strongly non-ergodic. There's really lots of notions of conservation loss in the system. And so that's like one of the simplest limits where it's strongly non-ergodic. You can take the opposite limit where every parameter is simply purely generic. So we choose the phase to be generic. We choose the one-side unitaries to be generic. And in this case, there's generally no correspondence between the singular values of the matrix and its eigenvalues, because this is not a Hermitian or not a unitary matrix. So we don't expect any of the singular values to also be eigenvalues. So we can only make use of the fact that these gates are unitary. This allows us to construct only a single non-decaying eigenoperator, which looks like this simple contraction here, which is some summation, again, over diagonal elements. You can see that if I act with my quantum channel on this operator, I can simply use unitarity to simplify it and get some eigenvalue 1. Again, precise details don't really matter. Just now, if I now project on this single state, which I'm going to get for a purely generic unitary gate, then I have this single projection here, which is simply taking the trace of my initial operator and the trace of my final operator. So there's no correlations anymore between my initial and my final operator, which is what you expect when you get thermalization to some infinite temperature state. And you can actually make this more specific here, but I'm not going to go into more details. So again, by tuning these unitaries, you can tune the amount of conservation loss in your system which is going to determine your steady state through the eigens, through the projection on the eigenoperators. Now we can kind of interpolate between these two limiting regimes, where I choose my u, so my left unitary, to be equal to my right unitary, only within some subspace. So I take these to be block matrices, where I take, for example, the first n diagonal elements to be, sorry, the operator just acts as identity within the first n elements, and that is some generic unitary within the remaining ones. And I can introduce some global unitary transformation W, which isn't really going to change anything. So if I do this, I can see, I can just plug this in my parameterization again. And now within this, this non-ergodic subspace, so the first n states, diagonal elements are again conserved. For the q minus n remaining diagonal elements, these are no longer conserved precisely because of the reason we had before. And I can show now that the long time value, if I again only project on these conserved operators, so these conserved diagonal elements, that if I act on some initial operator with my quantum channel and take this limit to infinity, I can write a steady state in this way. So I have some exponent of some chemical potentials mu a times Ca, and Ca is here exactly these diagonal matrices up to this unitary transformation I can just include in my block matrices. And so I can write a steady state purely in terms of the conserved quantities, and these chemical potentials mu are completely fixed by the initial state. Then this might seem like a very trivial result and not very interesting, but this is something you expect in generic many-body dynamics with conservation laws. But there it's extremely hard to prove that your steady state looks like this. Again, because of the exponential Hilbert space and because it's very hard to simulate generic many-body dynamics. So we can also add some perturbation on there to have almost conserved quantities, which I'm not really going to go into a lot of detail. You can just add a small generic unitary on the left and on the right, choose them to be different. You add some small perturbation on your leading eigenvalues. And this is then going to set the time it takes for you to reach the steady state value. So at short times, for a small perturbation, correlations aren't really sensitive to this perturbation strength. So if I here plot these light cone correlations as a function of time, these look exactly the same in this top panel, which is just a linear scale. So you might expect the effect to be perturbative. And if I plot this on a logarithmic scale, I can see that at long times, if there's no perturbation, my correlations go to some non-zero value, which is the GGE value, which I can just calculate from the conserved quantities. Then if I add a small perturbation, none of these conserved quantities are exactly conserved anymore. So these are going to decay with a time scale simply set by the perturbation strength. And this is just going to show that we can have lots of different non-trivial dynamics, even within this dual-unitary circuit, despite the fact that you might think that everything is built on the swap gate structure, but there's much more in there than you expect. Also, this is just something for people that are interested in many-body chaos. One usual indicator of whether a system is chaotic or not, so whether it has conservation laws or not, is by looking at the eigenvalues and looking into their statistical distribution. You just quantify this by this so-called R value, which, again, I'm not going to go in detail. It just takes one value for ergodic systems, which is this random matrix value of about 0.6. And for non-ergodic values with conservation laws, it takes this Poisson value of about 0.39. We can see that if you have some finite systems, which is here just, I think, 6 sides, if I change the strength of my perturbation, I clearly change from the non-ergodic value to the ergodic value. So you can also have this notion of pre-thermalization in here. Okay.
Peter,
yes.
The previous studies, is this a numerical study or is it an exact studies?
So this is exact, as in we can just diagonalize. So yeah, these dynamics can just be updated to arbitrary times just by diagonalizing these matrices, and we know their eigenvalues, because I think this is just for a local three-dimensional Hilbert space, so we can easily diagonalize them numerically and see this evolve. We can do some perturbation starting from the known non-ergodic result to see how the leading eigenvalue scales, and we can immediately represent all timescales in terms of this leading eigenvalue. So all of this here is pretty exact. And of course, this calculation for level spacing ratios is of course purely numeric, because I wouldn't know how else to do it.
Yeah, thanks.
Okay, great. One result I just want to show, but which I'm not really going to discuss, is you can also have correlations that are simply oscillating in time by choosing unitaries appropriately. But I'm not going to really discuss this. I just want you to be aware of this because I think it's quite interesting. It might also be something that other people might want to look into. But so what we've seen is that we can have these correlations within our dual-unitary circuit, they're 0 outside of the light cone, they're 0 inside of the light cone. If you have generic ergodic gates, then actually all correlations are simply going to decay to 0 eventually. So you might expect that nothing is really going on at long times. So that brings me to some other measure, which is namely out-of-time autocorrelators, which was also the subject of my first paper on this subject. So we're really interested in probing unitary operator dynamics. So we have some operator on a single site, which we evolve in time. We can do this by looking at correlators, but we can also look into out-of-time autocorrelators, which is something that people have been interested in through the connection with the scrambling of local information. So instead of simply taking the trace of rho times sigma, I'm going to be taking trace of rho times sigma times rho times sigma. And this is something that people have studied in chaotic systems, where there's some generic profile expected. So again, this is going to depend on both time and distance. What we see is that as a function of time, these again propagate with some finite velocity, which is here the butterfly velocity. And you have some profile, which is 1 inside of the light cone, 0 outside. And it goes from one to the other with some profile which widens in time. And the width depends on the dimension you're working in. Just for one-dimensional systems, which is the ones we're interested in, this is going to this profile, its width is going to grow as the square root of time, so diffusively. So this is what happens generically, but in fact, what's going to happen in dual-unitary circuits is completely different. So you can again do this derivation of a graphical expression for the out-of-time autocorrelator in the same way we had before. So now instead of simply having rho sigma, I have rho sigma, then rho sigma again. I can use unitarity to again introduce this hourglass shape centered on rho. Again, removing circuits. I can do the same thing, but now centered on sigma. Again, remove a large amount of unitary circuits to have something that can be written in a much more manageable way, namely something looking like this. And so we have 2 copies of our initial operator on the left, 2 copies of our final operator on the right. Now we just have some number of layers, some number of rows with 2 copies of both the unitary gate and its Hermitian conjugate. And the number of rows is going to be set by t minus x, so the distance of your second operator from the edge of the causal light cone. So that's the first thing to notice here, is that this diagram doesn't automatically evaluate to 0 when we're inside of the light cone. And the number of columns depends on t plus x, which is some kind of proxy for your total time. So again, if we're interested in the long time limit, we can just take the number of columns to go to infinity, which means that we can just identify a transfer matrix instead of some simple quantum channel, which you can write in this way. So again, the number of copies of the Hermitian conjugate of our gate, copies of our gate, and then repeat the same thing because we're working with 2 copies of our system. And now we can again use dual unitarity and our parameterization to see what are going to be the eigenvalues and eigenstates of this quantum channel. So the derivation is exactly the same with some slight subtleties, but none of them really matter for this talk. For example, if I calculate this quantum channel, to calculate correlations exactly on the light cone, out-of-time autocorrelators exactly on the light cone. So I only need a single copy of each. I can plug this in. Again, I know the singular value composition. Singular values are again this sum over phases, which can be 1 or can be smaller than 1. The diagonal, so the eigenstates of the entangling part are simply these basis elements with a single non-zero matrix element. And then here, again, I have a unitary transformation only set by a single one-side unitary U. And then here at the bottom, I have another unitary transformation set by the remaining unitary one-side unitary operator V. This is just to say, we again know the singular value decomposition of this transfer matrix, and we can tune it by tuning the parameters in our system. So we can again consider these limiting cases. Also, where we had Q singular values before, now we have a number of singular values equal to 1 that grows quadratically. Not that relevant, but just want to point it out. Again, just take U and V to be equal to 1, which means that all diagonal elements are conserved. And so we can show, well, it's actually slightly more subtle, that the eigenoperators now don't decay. So single non-zero element A, B, C, D. If A equals B or C equals D, then we can check in this phase simply cancels with this one cancels with this one. So I'm going to have eigenvalue 1. Or I can also have this one canceling with this one, and this one canceling with this one. So I have quite a large class of non-decaying orthonormal eigenoperators. I can calculate the steady state value by projecting on these corresponding eigenoperators. And I again have something that depends very strongly on both my initial state and my final state. So the OTOC also has some notion of non-ergodicity here, where the steady state value is going to depend strongly on the initial and final operator and the conservation loss you have in the system. You can just plug this here. So here I've just chosen 4 generic operators, evolve them in time. These are the out-of-time autocorrectors on the light cone as a function of time. You can see they all reach a steady state value. We can calculate the steady state value, which is simply this dashed line. You can take the opposite limit, where you don't impose any structure on either our phases or one-side unitaries. And actually, this is a kind of systems where the transfer matrix was already considered before by Bruno Bertini in this paper that introduced maximally chaotic unitary gates. So I'm sure he'll tell you more about this later. But now, by making use of both the unitarity and the dual unitarity, we can construct 2 different eigenoperators. Again, by now simply contracting this and making use of unitarity or dual unitarity. And they look like this, and you can orthonormalize them and introduce appropriate projectors to find the steady state value of your OTOC. And now if you do this, you actually find that your steady state doesn't have any correlation between your initial operator and your final operator. It only really depends on the dimension of your Hilbert space. And so you see for different operators, all these OTOCs decay to the same value. So all information is really lost here. And again, you can interpolate between these 2 different, very limiting behaviors by imposing some block structure on the one-side unitaries. So we're keeping the non-ergodic dynamics within a certain subspace, and we're mixing everything within the remaining subspace. And if we do this, perhaps not surprisingly, we get 2 classes of non-decaying eigenoperators. So we have these basis states, which are simply, again, a single non-zero matrix element. Same ones, but now all initials need to lie within this non-ergodic subspace. So we have 1 to n, just identity here. So these can take n different values. And we can take these contractions, where now these are simply contractions only with an additional projection within the ergodic part of your space. So it really projects here on this remaining part where you don't act like identity. So these are a direct generalization of the eigenstates we had both for the non-ergodic case and the ergodic case. You can also see that they don't have any overlap with each other. So we can just write the projectors as first a projector on the non-ergodic basis states plus a projecting on the ergodic part. And we simply see that we have some decaying thing, and the final steady state value has both a constant contribution and a contribution that depends on the operator you're considering. So in this way, we have something that's still non-ergodic. Again, good it's for observations, but I'm not going to go into this. So we can also go inside the light cone. Things get slightly more complicated, but not that much. And in the non-ergodic case, we can simply see that everything immediately saturates within the light cone, and the transfer matrix becomes effectively a projector. So everything is constant up to some parity effects, which you usually have in these unitary circuits. If you have an ergodic case, things decay exponentially to 0 inside of the light cone. And so in all of these models, we can see that the most interesting behavior is exactly on the light cone. So the butterfly velocity is maximal. And so the qualitative behavior you get here is completely different from the one you expect for a chaotic model. So you don't have any widening. You have a butterfly velocity, which is the largest value you can possibly take. So in this way, the results we got for correlations are somewhat generic, as in you can expect them to see also in generic many-body systems. But if you calculate these OTOCs, they're very much non-generic and kind of indicative of the fact that something more is going on. And this has also actually been experimentally measured by Google in their Sycamore processor. So we have this maximal velocity. And so what I've shown here, every picture is a single realization of their Sycamore processor. Every circle is a single qubit. And they somehow managed to find a way of directly measuring the OTOC between some initial site, which is the black site, and all other sites. And so every realization here is the evolution with some gates. And top row corresponds to evolution with an I swap gate. The name kind of tells you that this is going to be a dual unitary gate. And the bottom row tells you about what happens if you do some evolution with a square root I swap gate, which is not a dual unitary gate. And because we don't have a simple one-dimensional system, the edge of the causal light cone isn't simply going to be the straight line, but it's still given here in terms of this dashed line you see everywhere. And you can clearly see that the OTOC in the dual unitary case is immediately non-trivial and non-zero at the edge of your causal light cone. So you again have this maximal butterfly velocity. Things spread out very quickly. So after 15 cycles, your information is completely scrambled over the entire system. The OTOC is non-trivial everywhere. On the other hand, if you look into this bottom row, you can see that the O-talk spreads much slower. At the edge of the light cone, nothing is really happening. And even after 22 cycles, you're still not close to hitting the edge of your system. So these dual-unitary properties, while reconvened in 1D systems, can also be probed in this way into more involved systems. And I think within the rest of my talk, I'm going to give some exploratory results for seeing how stable any of this is in a specific class of dual-unitary gates. Because the general formalism for this, so does dual-unitary survive perturbations, is going to be outlined in the next talk by Thomas Prosen. But here I want to consider a very specific case. And also you can see this paper, which I'm sure he's going to talk about in a lot of detail. So we had this quantum channel, this transfer matrix approach for OTOX. We had this quantum channel for correlations on the light cone. We had transfer matrices for OTOX both on and inside the light cone. Now, if we no longer have dual-unitary gates, we can still construct a higher dimensional quantum channel to calculate correlations inside of the light cone. So this is the kind of expression you would get if you just take a single step inside of a light cone. Again, the number of copies of unitary gates you get is going to depend on how deep you are inside the light cone. And this is going to grow linearly with the distance from the light cone, which means that the dimension this acts on is going to grow exponentially. But we can again identify a transfer matrix. And I'm going to be considering a very specific class of unitary gates, which have a very interesting limit where they're dual unitary. So I take my unitary gate to be consisting of 4 different parts. So again, I have some entangling part and some one-side unitaries. Now I don't take the one-side unitaries to be generic, but rather I take them to just add some phase to my Z component. So again, now I'm working with qubits. So this just gives some phase to either 0 or 1. And the entangling part, rather than considering a swap gate with added phases, is now going to be a linear combination of a swap gate and identity, which anyone who's worked with integrability is going to be familiar with this. So we have some parameter lambda, which sets the linear combination between the identity, which is represented here by these 2 straight lines, and the swap gate, which is here represented by these 2 crossing lines. So if lambda is 0, my unitary is simply the identity, which means that, sorry, just going to take a quick drink. If every single unitary is identity, then correlations aren't going to propagate at all. They're just going to stay fixed. Whereas if lambda goes to infinity, I'm going to put a swap gate where correlations propagate with the maximal possible velocity. And the question is, what happens in between for these systems? So we really have 2 different limiting cases. And now the question is, do we just interpolate between the 2? Or is there still going to be some trace of dual unitarity, so this maximal velocity in between? And so I'm going to be taking a circuit, so a quantum channel, where each of these circuits has the same value of lambda, so the same entangling part, but the one-side unitary, so these random phases are going to be chosen differently. And you might think that these are just random gates, but we still get these from a circuit. So for example, this gate is related to this gate by Hermitian conjugation. Same thing for this gate. So in order to make sure which gates are related to Hermitian conjugation, I can use this folded picture, which I'm sure is going to show up in later talks. It simply takes one copy of my diagram and just slowly fold it over. So it's really just showing gates acting on doubled copies of the Hilbert space. So we again have some kind of transfer matrix we can calculate, and now all correlations is contained within a single site. And now what I'm going to do, I'm going to reintroduce this parameterization. So everything has the same entangling gate, the same R matrix, with some random one-side unitaries. And each have a different random angle. Now what I'm going to be doing is I'm going to make the assumption that the evolution after a long time with all these random phases is going to be the same as the evolution of the average circuit. So if I just average this transfer matrix over these phases, I can just evolve it in this time. And if I do this, if I average every single one-side unitary, these essentially become projectors on a very specific subspace. If I construct, and so I can work in this projected basis, I have, again, some boundary conditions. And these gates now are simply these double gates I had before, so these doubled R matrices, projected into the space that we have from the one-side unitaries. And if I write this down, I actually find a classical stochastic model that everyone who, again, is familiar with integrability will recognize as simply, again, an R matrix, but now a real one. And so people are very familiar with working with classical stochastic models with transfer matrices of this form. So we can exactly find the long-time correlation within this average circuit. So if you have any questions, you can ask me about this after talk. And we can do this evaluation here. We can evaluate the correlation functions even inside the light cone, use it for this classical stochastic model. We can write these as a hypergeometric function, which is looking something like this, which isn't very intuitive. Then if you scroll through the literature, you can find some clear asymptotics for these functions. We find that at long times, the correlations within this system look something like this. So we have two parts. So first is exponential part minus x squared over t. Here you see here there's a dependence on lambda, where if lambda is 0, this is going to dominate, where if lambda goes to infinity, this is going to be 0. And then some additional contribution, which you might not expect. And in order to get some more insight into what's happening here, we can simply plot this correlation profile for different values of this parameter lambda, so setting how strongly it's non-dual-unitary, and show this at some fixed time. So we let our system evolve over some fixed time, and we calculate correlations everywhere inside the light cone. So for every distance x from the light cone, and we can see that if lambda is small, so it's very close to identity, correlations are still very strongly peaked at the origin and spread out almost diffusively, so with this Gaussian profile. But if lambda becomes larger and we move towards the red and the purple line, you can see that the correlations are peaked some position inside of the light cone. You can actually show that correlations are peaked at some distance x equal lambda squared, and they propagate with a maximal velocity until they've reached that position, which is kind of similar to an Ornstein-Uhlenbeck process. We have some particle that experiences both drag and random noise. I think this probably illustrates what's happening better. So it's just some heat map of the correlation. So this yellow line is the light cone. I have some particle that starts from the upper row here, so originated at the origin. And their correlations quickly spread out along the light cone. And after some finite time, they're going to start spreading diffusively after this point. So they first propagate with maximal velocity until they've reached some position. And after that, everything is really dominated by just diffusive spreading, which is all just to say we can still see some trace of dual-unitarity. If we look into some time t equals lambda squared, which is going to be infinite if we have a pure dual-unitary swap gate, then we're always going to see this maximal velocity. If it's not exactly a swap gate, but if you have some small perturbation, then at long times these things are just going to look diffusive, but spreading out from some finite distance. And that concludes my talk, where I basically want to show you that we have this efficient parameterization of a class of dual-unitary circuits, and we can tune these to return either ergodic or non-ergodic dynamics, and in this way fully characterize the correlations to the quantum channels and the OTOX through these transfer matrices. And this way we can connect these with the general many-body phenomena of both thermalization and scrambling, so how a system relaxes to equilibrium, and in what way local information is lost. And then, as we have these in the last part, I show you how we can use tools from integrability to study a very specific class of perturbed dual-unitary models. So with that, I'd again like to thank you for your attention and thank the organizer for allowing me to talk about this. So I think we have time for questions, I hope.
Yeah, indeed. Thank you, Peter, and thank you for sticking to the time. We do have time for a couple of questions. So are there any questions?
Can I ask a question?
Yes, please.
Yeah, sure. Go ahead.
Yeah. So about this last part. So
Yes.
there where you, I mean, used integrability, right, to
Yes.
access this non-dual unitary. So that was necessary, right, to get some results.
So yeah, we wanted to find some model where you could exactly calculate, so evaluate the diagram looking like this. And there exist general techniques for this, and I don't want to spoil too much of Tomas's talk, so, which is why I'm not saying much more about this. But actually, these correlations, we didn't really need to use integrability because this is a very simple expression. If we would want to evaluate more general correlation between, for example, 2 operators or 4, then we would need to use integrability. But so far, the fact that you can get a hypergeometric function like this, we could use some combinatorial methods that didn't really rely on integrability. Just so happy that this gate we found originated from integrability. So there might be other gates that get mapped to similar classical stochastic models where you can do a similar evaluation, but I don't know of any right now.
But I think it's crucial that the classical stochastic map is Young-Baxter integrable, no?
Yes.
Yeah. Thank you.
Peter, just a comment on the kind of I mean, the operators which you chose here, the R matrix,
Yes.
they are powers of swap. Is that something which is significant here?
Okay, so they're not exactly part of swap. So you have the swap gate, but you also have some correction which is equal to the identity. And so the identity is very much non-dual unitarity.
Yeah,
So
but these are fractional powers of swap.
I'm sorry?
These are fractional powers of swap. So what was showing?
I hadn't thought of it in this way.
Yeah,
So
they just interpolate from lambda equals 0 identity. So they just s to the power.
Okay. Yes, you're completely right. Yeah, of course. Now I see. Yeah.
So that's very interesting. So I have another question about the level spacing statistics which you showed.
Yes.
So that is for some finite number of particles with boundary conditions.
Yes.
Is that something which is stable against number of particles? Is this epsilon something which is
no?
No.
So yes, exactly. So that's something which I didn't mention, but it's very relevant. So the moment epsilon is non-zero, you're going to have an ergodic system. So you expect Poisson level statistics if you have you expect random matrix statistics if you're already working in infinite system size. So the fact that we have some regime where the system behaves Poissonian, I mean, in the level spacing statistics, is purely a finite size effect. And you can see that if I increase the dimension of my local Hilbert space from 3 to 4, epsilon is the set, then the point where you transition from Poisson to random matrix reduces. So if I would immediately have an infinitely large Hilbert space, then there is no value where we get Poisson statistics.
But just for sticking to, let's say, Q equals 3,
yes.
Is this epsilon, is it like an MBL? Can you interpret it like a MBL transition or something?
No, but because this is for a this is for a fixed number of sites. So this is for 6 sites and 2 evolution steps. But if I would include more sites in the support, we'd see the same thing, where you'd also have this transition occurring at a lower value.
Okay. So it's not only with Q, but also with the number of particles it scales down.
Exactly.
Okay.
Yeah.
So maybe then for all dual unitaries, epsilon non-zero is immediately ergodic or GUE.
Yes, if you have an ergodic unitary circuit, then I expect the level of spacing statistics to be random matrix, which is also kind of interesting because usually in many body systems you expect these random matrix statistics, but dual unitarity, they're exactly solvable. In exactly solvable models, you typically expect Poisson statistics, which here clearly isn't the case. So the interesting thing isn't that we get these Poisson statistics at small epsilon. It's more the fact that generically we get these random matrix statistics.
Just one more question.
A short comment.
Yeah.
A short comment on that. You can actually prove some of these statements for dual unitary circuits. I will discuss that in my talk. So you can actually prove that for generic dual unitary circuits, you have random matrix statistics.
Okay.
Yes.
Just a very quick question about the OTOCs.
Yes.
Can you also see a Lyapunov exponent in the root space?
No, not really. So we tried to extract some kind of Lyapunov exponent from there, but we couldn't.
Okay. Thanks.
Okay.
Thanks for an interesting talk.
Thanks.
Thank you. Thank you, Peter, once again.
Stop sharing.
And maybe any other discussions, we can do them offline. And I think we have the next speaker here already. Thomas Brosen is here. So can I request you to share slides, please?